For Lab 2, I dropped my favorite stitched scrunchie off the second floor ledge onto the staircase in my house. I dropped the scrunchie from rest and observed it fall somewhat slowly in comparison to how fast a rock would have fallen if dropped from rest at the same height. As a reminder, here are some fundamental formulas for Lab 2. All calculations were to prove the first net force formula, displaying the work of both gravity and drag forces against the scrunchie's fall. The second formula, Newton's second law, or the momentum principle, is the foundation for all calculations in this lab, including the velocity calculations, which we'll discuss in a bit. Finally, the position update formula is helpful for the dropped calculations. A quick note before we dive into the video and further calculations, I am acknowledging that the scrunchie does have a small hole in the center for tying up hair, which ultimately affects the fall as it allows air in the center or less drag. To begin with, we will only consider the effects of weight force or gravity as the scrunchie falls, as shown in close script. When considering only gravity, it's important to note our proportionality constant is set to 0. Gravity is still set to 9.8 here. So when we run this, here's our output. Next, we'll see how the drag force is equal and opposite to the gravitational force. And since it's falling, it is opposite to the velocity. Here in glow script, we can see the effects of gravity plus the drag force this time around. Just as a general acknowledgement, we used the drag force as being proportional to the object's velocity, and then later the drag force was proportional to the square of the object's velocity. So here we quickly run through. After some trial and error, we found that the best proportionality constant would be B equals 0.1, given our arrow scale being 2.04 with some quicker calculations. And when we run this program, we see in the teal color the drag force pointing up against the orange gravity pointing down. Here we see the final output for the falling stitch scrunchie given the experiment position and tracker, the model position of gravity plus drag, and the model position of gravity only. Here we can see they're all fairly similar. There was some variation with the tracker position, and this is due to the previously mentioned fact that there was a hole in the center of the scrunchie which messed with the drag force. The gravity plus drag model demonstrates terminal velocity. Terminal velocity is when a freely falling object eventually reaches a constant speed against resistance. The slightly curved line, as seen here, is how we would know. Since terminal velocity happens when the force of drag pointing up has exactly balanced the force of gravity pointing down, this means that the net force will equal 0. So, if the scrunchie was initially thrown downward, the terminal velocity would be the same from the case where the same scrunchie was initially dropped from rest. So using GlowScript, I adjusted the ball.vel vector from 0, which shows starting at rest, to ball.vel vector being -2 in the y component to simulate a downwards thrust. Additionally, I extended the time while loop from being t less than the final recorded time, which was 0.878 seconds, to t equals 5 seconds. This larger time window shows, as graphed here, how the velocity versus time graph eventually curves and levels out as terminal velocity would. So finally, in conclusion, we can see that when the net force equals 0, we are sitting at a constant velocity. We learned that the net force equals the force of gravity plus the force of drag. Putting this together using F net as 0, we can set 0 equals to the force of gravity plus the drag force. This means that gravity is equal and opposite to the drag force. Changing the initial velocity will not change the relationship between the force of gravity and the drag force. Terminal velocity stays the same regardless of if the scrunchie was dropped or thrown off the railing.